At any rate, last day I did have you look at some compounds, and I had you look at dissociating some compounds that were actually low solubility. So in fact, they would not dissociate, they would be solids. And solids, of course, the ions are bound together, they are not dissociated. However, you need practice with lots of compounds. So I gave them to you even though they won't actually dissolve. Now, in grade 12, you will learn that they actually do dissolve, but only the tiniest bit. So you might have magnesium hydroxide, and no matter how much you dump into the water, it has a maximum concentration of 0.001 molar. And so the concentration of magnesium would be 0.1, and the concentration of hydroxide would be 0.0002, sorry, 0.0001 and 0.0002. It is still a 2-to-1 ratio, but the concentrations are super tiny. So should you be writing those dissociations in grade 11 for a solid? Probably not. But is it good practice to write dissociations? Yes, it is. Today, however, we are going to do complete and net ionic equations. And in this case, anything that is a solid is going to stay together. And anything that is aqueous is going to dissociate. And those are hard rules this week. Those are unbreakable rules. Okay, so like last week, I was sort of like willy-nilly, oh yeah, just dissociate everything. Here this week, anything that's solid does not get dissociated. Anything that is aqueous does. Okay, so our ionic equations, get rid of all that. In our aqueous AgNO3, the silver and the nitrate are dissociated, right? We get our silver is separate from our nitrate. They are both aqueous. Okay, and our sodium is actually floating around separately from our chloride. So you can actually write them separately, and this is one of the things we're going to do a little bit later. And then when we get our products, and I'm going to scooch way on over here because I ran out of room there, we have AgCl, which if we go and look on our solubility table, AgCl, here's our chloride, here's our silver. That is low solubility, so that means that AgCl is a solid. So we can go back here and say, okay, that is a solid. Now, how about our other product, which would be, hi?
What? I don't understand why that would be a solid.
Because according to our table, when you put silver together with chloride, it is low solubility. Soluble means it can dissolve in water. Okay, but if it says low solubility, that means it doesn't dissolve in water.
Like not 100% of it.
In water, very, 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 very little. Okay, and for grade 11, you can just assume that it doesn't dissolve at all. In grade 12, we'll say yes, it does a little tiny bit, but for grade 11, just say no. Low solubility, it doesn't dissolve at all. It is just solid. Can you imagine taking a piece of chalk and throwing it into water? Does it dissolve?
Not fully.
Not really.
No, it really doesn't. And if you take something like sodium chloride, it will dissolve in water. So low solubility is something like chalk that does not dissolve. And soluble means it can dissolve, which means that it is aqueous. Did that answer your question?
Yeah, that makes sense now.
Okay, cool. All right. So let's go back here. So the silver chloride, we looked it up, it said low solubility, so it is solid. But now we need to go check on sodium nitrate. So we go to our table of solubilities and we look up, usually we'll be looking up our anion first, and in this case we're looking at nitrate, and oh my goodness, with everything it is soluble. That means that the sodium nitrate will be aqueous. Had we looked up the sodium, we would also see that alkali ions are soluble with everything. So again, that just proves to us that our NaNO3 is aqueous. Now, if the NaNO3 is aqueous, you can actually see that in our little picture here. The NaNO3, the ions are still dissolved. They're floating around, right? They are aqueous. And in fact, instead of writing NaNO3, I could write Na plus, floating around separately from the NO3 minus, okay? However, this little chunk right here is silver chloride. It has formed a solid, so what you'll see is you'll see a precipitate. I don't know if you remember, we had that one little demo we did where we poured the two things together and we got a solid forming. It was yellow, okay? And yeah, so then you have a solid. Now, that solid that forms is called the PPT, which stands for
Precipitate.
precipitate. Yes. Okay. So today we are going to write 3 types of equations around a precipitation reaction. First thing we're going to do is we're going to write the formula equation, which is the one we've always been writing. We had silver nitrate. Maybe I'll write in black. That'd be nicer. We had silver nitrate. Whoops. Sorry. Silver nitrate. So we're writing the formula of the compound, and it is aqueous. We're going to write the formula of our other compound, and our other compound is sodium chloride. So we have sodium chloride aqueous. And in the assignment that you have, this sheet is in there and it is all filled out. So you'll see actually these compounds and everything are pre-filled in on your copy. So you don't have to copy this down if you don't want to. Okay, we did our double replacement and we got silver getting together with nitrate. And we decided that was a solid. And we also got...
Wait, hold on. Stop right there.
Nope, not silver with nitrate. You're right. Oh dear, it should be silver with chloride. Yes, thank you so much. Okay, that looks better. And now I've done things really wrong here. That's why.
I knew I'd see that.
Holy man. Okay. I think we're right now. I think we got it. Thank you so much. Okay, and the sodium is then going to get together with the nitrate, NaNO3. And this particular one was really easy because everybody had a +1 charge or a -1 charge. AgCl minus, Na plus, NO3 minus. So we didn't have to worry too much about writing our formulas. Okay, we will in later questions. Okay, and that's aqueous. So this is called the formula equation. We will sometimes, I get lazy and I call it the FE for formula equation. I've got some extra videos for you to watch if you're having trouble with this later on this week, and in some of them they call it the molecular equation instead. So formula equation and molecular equation are the same thing. So that is what we would normally write. However, if we look in our beakers, we can see that we really have, well, I don't have AgNO3 stuck together. What I have is I have little Ags floating separately from little NO3s. So I have Ag plus, which is aqueous, floating separately from the NO3 minus, which is aqueous. I also have my sodium chloride, which is aqueous, and whenever it is aqueous, those ions float around separately. So to write the complete ionic equation, which is what this is, we separate our ions. So Na plus, aqueous, is separate from Cl minus, aqueous. Okay? And now in our products, our first product is a solid. Okay, so do solids come apart or do they stay together?
They stay.
They stay together, so I don't separate that. I just write AgCl, solid, and then NaNO3 is aqueous. So when it's aqueous, it dissociates, just like that worksheet you were doing last week. So you'll end up with an Na and an NO3. Na aqueous plus NO3 aqueous. Okay, this particular form includes all of the ions. So it is complete. So we call it a complete ionic equation. In some of those videos I told you about, if you want extra help over the week, they call it the total ionic equation, or sometimes even just the ionic equation. Okay, so when you want to write the complete ionic equation, what you're going to do is you are going to separate all the aqueous ionic compounds into their component ions, but you're going to leave the solids alone. So you can see silver nitrate was aqueous and it got split. Sodium chloride was aqueous and it got split. Silver chloride is a solid and it stays together, and NaNO3 again split apart.
How do we know that Ag and Cl go together from the long equation?
Okay, so like from this one here or from the one above it?
From the blue.
From the blue one, okay. You know that because you've previously written the formula equation. So the steps in this process are going to be that number one, you're going to write the formula equation. And in doing so, it's gotten really messy now, but you'll see it's a double replacement. And if we have a double replacement, the silver has to swap partners. So it's going to get together with the chloride anion. Yeah? And the sodium is going to swap partners. So it's going to get together with the NO3 anion.
So we'll never be given an equation that looks like the blue.
No.
Okay. Okay.
Okay, you're not going to be expected to predict the products from the blue one. No.
Okay. Yeah.
Okay? Yeah.
Yeah.
Good question. Okay. So that's our complete ionic equation. So that's the next thing we do. Now, the Ag and the Cl, I want you to focus in on those right now. We have our Ag and we have our Cl, and they start out as free-floating ions, but where are they at the end? They are a solid. So the silver and the chloride actually underwent a chemical reaction and became something completely different. We produced a new chemical. There's been a new substance produced. And so Ag plus and Cl minus underwent a chemical reaction. Okay, because they started out floating around and now they're not floating around. Now we have a solid, so a new substance was produced. But what if we look at nitrate? It was floating around and now, oh, it's still floating around. If we look at sodium, sodium's floating around. Oh, it's still floating around. Did sodium and nitrate make a new substance?
Absolutely.
Did they?
Or
They were floating around as ions. Now they're still floating around as ions. Are they any different than they were before?
No.
No, they are no different than they were
They're the
before.
same.
Okay. So the Na plus and the NO3 minus didn't change at all. First, they were in two separate beakers. Now they're in the same beaker, but that's a physical mixing process. That's not a chemical change. We did not get a new substance. Okay, they were physically mixed. But there was no new substance. So what we do is in the next form of the reaction, we are going to write a third type that shows only the species that are reacting. So who are the only things that are reacting in this chemical reaction? Who are the
AG,
only
CL.
things? Yeah, the Ag and the Cl. So we're going to just write Ag. And remember, it has to be Ag plus. Okay, it's not a neutral atom. It is a positive ion. And the Cl minus get together. And they form AgCl solid. And we call that one where we show only the species that are reacting, we call that the net ionic equation. Now, we can get the net ionic equation fairly easily from the complete ionic equation. Let's just go back briefly to our complete ionic equation. And I'm going to erase some of this nonsense because it's just making it horribly messy. There we go. Okay. Now, one thing you can do is you can see that you can go through and you can circle things that have not changed from one side to the other. You can say silver, or silver has changed. Sodium, however, it was Na plus over here and it's Na plus over here. It did not change. NO3 minus over here, it's still NO3 minus over here. So you don't actually have to have your beakers all drawn out showing you that the sodium didn't change and that the nitrate didn't change. You can just have that in the complete ionic reaction. Now, we call these ions that don't actually participate in the reaction, they have a name. What do you call people who go to a baseball game and they watch it from the stands, but they don't participate in the game? They are not the baseball players. What do we call those people watching the game?
Fans.
We call them fans, but there's another word we could use.
Spectators.
We could call them the spectators. Okay, and the spectator ions are ions that are not involved in the chemical change. They just watch the other people react. Ions that don't react. And what we do is we take our complete ionic equation, we identify our spectator ions, and then we cross them out. And when we cross them out, what we are left with is, that was supposed to be highlighting. We are left with Ag plus Cl minus goes to AgCl, which was our net ionic equation. Okay? So 3 types of equations. Formula equation, all the formulas are written together. Nobody is separated. Complete ionic equation, everyone who's aqueous separates, everyone who's solid stays together. And then for our net ionic equation, we cancel out the spectator ions. Now, you might get a reaction like this one. I have some sodium chloride, okay, and I have some potassium nitrate. All right, and I mix them together, and if I go to my solubility table, Oh, that's not, is that the one? Yeah, it is. Why is it so in the wrong place? Makes me sad. Oh well. There we go.
There you go.
Yeah. So anyway, we had potassium nitrate, and we had sodium chloride, and we reacted those, and we would get potassium chloride. But let's look at what happens when I put potassium with chloride. Potassium with anything is soluble. So my product is aqueous, okay, my first product. My K getting together with my Cl. My sodium cation is going to get together with my nitrate anion, NaNO3, aqueous, because sodium is soluble with everything. So my products are both aqueous. And we can see that if we go back here and we look and we say, oh, look, everybody is aqueous. Everybody is still dissolved. Has anybody changed at all from start to finish? Have any of the ions become something different?
No.
No, they have
No.
not. Okay, so because none of the ions have become anything different, because they have not become anything different, there was no
reaction.
reaction. Do you guys remember this from earlier? You used to write NR for no reaction, and that's when both of your products are aqueous, okay? And notice that it doesn't matter how you list the products. I could write KNO3 plus NaCl gives KCl plus NaNO3. Or really, if I wrote it as NaCl plus KNO3, is that any more or less valid? No, because I didn't actually make anything new. Now I've just got a mixture of all these things together. Okay, so what would happen if we actually wrote a formula equation for this? Everybody would just be aqueous. NaCl aqueous, 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 aqueous. So if we write our complete ionic equation, everybody who's aqueous breaks apart. Aqueous, Cl aqueous, K, NO3, aqueous. Oh, look, nobody changed. So to write the net ionic equation, we would write the spectator ions and cancel them, but everything cancels out. So there was no reaction. Okay, so don't worry about ones like that. You can just be like, oh, there was no reaction. You don't have to write the complete ionic equation. You don't have to write the net ionic equation. Just write no reaction. So when you come across one like that, you can be like, phew, easy times. Okay, this one is going to be more complicated. It's got lots of, you'll notice there's lots of little subscripts here. Okay, so we've got all kinds of different charges on things. So we're going to remind you how to write a double replacement reaction. So on the reactant,
Going to be on the sheet, or do you want
this is on the sheet. So you don't have to write it. Like each step of this is filled in on the sheet for you.
Sweet. Okay, thank you.
Yeah, yeah. So on the reactant side of equation, you're going to write the two compounds being mixed. So you've got CaNO3, CaNO3, 2, and you have Na3, PO4. Okay. Step number 2, you're going to identify the ions present and their charges. This is hugely important because otherwise you'll make a mistake in writing the chemical formula and then your reaction won't balance properly. So our ions are calcium, which you can look up. It has a 2+ charges in column 2. Nitrate, you can look it up. It has a -1 charge. Sodium is +1, and phosphate is 3-. Now calcium is going to get together with phosphate, and sodium is going to get together with nitrate. So everybody's going to swap partners, okay? Because sodium was originally with phosphate and calcium was originally with nitrate. So we're going to write our products then. So we have our reactants, NO3, 2 plus Na3, PO4. Our products, put calcium with phosphate. That is going to be Ca3, PO4, 2, because that way we'll have, if we have 3 of the calcium, that's going to give us a 6+ charge. And if we have 2 of the phosphate, that's going to give us a 6- charge. So that gives us an overall neutral compound, which is what we want. Okay, and then our next thing we're going to have is sodium is going to go with nitrate. They're both positive, they're both 1. Na is +1, NO3 is -1, so we just need one of each. NaNO3. And then our last thing we're going to do is we're going to balance the equation. And I can see right now that I have 2 phosphates. And if I put a 2 here, that gives me 2 times 3 is 6 sodiums. So what if I put 6 sodium. So if I put a 6 here, that means that I need 6 nitrates. Over here I already have 2 nitrates, so I can multiply that by 3, and that means that I have 3 calcium, and hopefully, oh look, I have 3 calciums, and everybody works. I didn't leave enough space here to do all the writing out of each species, but you can certainly do that if you want to, okay? So before you go on to anything with the complete ionic equation and the net ionic equation, you must have a balanced formula equation first, okay? So all of this is just for a balanced formula equation, FE for formula equation. Now we're going to write the formula equation including the states. So we have Ca, NO3, 2. You can assume that any reactants I give you are going to be aqueous unless I tell you otherwise. Assume, this is in the instructions on the worksheet, assume all reactants are aqueous. So you only need to look up the products. Plus 2 Na3 PO4, we're assuming that is aqueous. Now we need to go look up Ca3 PO4 2. And you always start by looking up the anion. Look up the anion. So let's go to the chart. Phosphate, we're looking down the left-hand column. So we're going to scroll down until we get to phosphate. There it is. And it is soluble with all of the alkali ions, which you might want to write this in for yourself. Those are lithium, sodium, potassium, rubidium, cesium, and francium. How can you remember those? They are given to you at the very tippy top of the table. Okay? But you can write them in where it says alkali ions for yourself. Now, we had calcium phosphate. So we do not have one of these. We don't have hydrogen. We don't have ammonia. So we are dealing with something that falls in the all others category. And it says that everything else with phosphate is low solubility, which tells me that this is going to be a solid. So we are going to get a precipitate in this reaction. So calcium phosphate is a solid. And our other one, NaNO3, is, and we can again go look that up. I'm not actually going to go to the chart this time because I know that all alkali are soluble, and I know that all nitrates are soluble. If you can memorize those, that's super helpful. You don't have to look at the chart all the time. But if you can't, they are on the chart for you, so there you are. Okay, and I forgot my coefficient here. Did I forget any other coefficients? I forgot my coefficient here. And in fact, I do want to put those in different colors just because it's going to make my next step a little tidier. Okay. 6 there and there. Okay. Write the complete ionic equation by dissociating, just what you did last week, the aqueous ionic compounds, but you'll keep the solid compounds together. Now there's a little trick here, and this is what you haven't seen yet. Use both the coefficients and the subscripts to tell how many of each ion. What the heck does that mean? Well, we have 3 calciums, and calcium does not have a subscript, so it's just going to be 3 calciums. 3 calcium. And the charge of calcium, remember, we figured that out before. It was 2+. Do you need the charges? Yes, you need the charges. It's wrong if they aren't there. This is an ionic equation, and ions have charges. Okay, now this next one, we have 3 nitrates, but I want you to take a look. What's that down there? We have 2 nitrates in that formula. So we have 3 times 2 is 6
6.
nitrates, right? So we're going to write 6 nitrates. So this is where I'm saying, yes, you have to use both the coefficients and the subscripts to tell how many ions. You can't just use one or the other. Okay. Next one, we have 2 times 3 is 6 NAs, and that is aqueous. Have I forgotten anything?
Hold on. Let's see here.
The charge.
I forgot the charge. Yep, absolutely.
Yep, remember.
Got to put that charge on there, okay? And then I have 2 of these. So is that going to be 12 PO4s?
Wouldn't it just be 8?
Would it be 8? Oh my gosh, would it be 8? Is it 8 PO4s? I'm being super tricky here. You have 2 Na3 PO4. How many PO4s do you have there in the formula? If we got rid of that 2, how many PO4s do we have? How many phosphates? Remember, phosphate is 1 phosphorus with 4 oxygens attached. How many phosphate groups do we have in this formula here?
1?
Just 1, okay? So when I do this, I actually don't have 2 times 4. I was trying to trick you there, okay? We just have 2 phosphate groups, okay? So that'll just be a 2, okay? And that is 3 minus. Now our next one, oops, I forgot my aqueous. Our next one is a solid. So what do we do with it? Do we take it apart or leave it together? Do solids dissociate or do solids, the ions, stick together?
Stick together.
They stick together, yep. So we have Ca3, PO4, 2, solid, all just stuck together. And then, and complete ionic equations are really annoying because they go on for a really long time. So let's see. Now we have 6 NAs, 6 Na plus 6 NO3. Anything missing there?
Charges?
Charges. That's Na plus, that's NO3 minus. Anything else missing?
The CaPO4 doesn't have a coefficient, or whatever you call them before.
Oh, like a number here? It doesn't need one because its coefficient is actually 1.
But what about the PO4 2? That doesn't matter?
The PO42, no, because it's part of a solid. If it came apart, there would be 2 phosphates. But it's stuck together, so you would have 3 calcium stuck to 2 phosphates.
I see. Okay.
Yeah?
Yeah.
Okay. What we're missing over here is actually the states. You have to include them, okay? Because it tells you whether you're separating them or keeping them together. Okay, and finally, we are going to identify our spectator ions. Can you see anybody who does not change from one side to the other? Which ions do not change?
The sodium. One is
Sodium,
the sodium.
definitely.
Yes, because that has not had any role in the reaction.
That is correct. And the other one?
NO3.
NO3, yeah. So those are our spectator ions. So we could say our spectator ions are Na plus and NO3 minus. We don't write 6 Na plus because 6 is just part of the balancing of the reaction. We're just trying to say who is the spectator. We don't say 6 nitrates are the spectator because in a beaker we'll have way more than 6 nitrates. So don't use the coefficient when identifying the spectators. So don't write like 6NO3 minus, don't do that. Because we've got way more than 6. We've got millions and billions and hexillions of ions. So yeah, so what we're going to do is we're going to cancel them out, cross them out, and we are going to write what is left over. Okay, so what is left over is we have 3 calciums, aqueous, plus 2 PO4, 3 minus, aqueous, and the only thing left on our product side is the Ca3, PO4, 2, solid. And that's it. Worksheet. This is what the worksheet looks like. The bottom of the worksheet anyway. And for this week, what I'm going to have you do is I'm going to have you do the odd letters only, which are bolded. And then next week, just to review, you're going to do the even letters, which are the blue ones. Okay, so in the first part, the formulas are given to you, and then in the second part, you have to come up with the formulas yourself.
I have a quick question.
Yes, certainly.
Yeah, Tricia, for the worksheet on
Yep.
number A,
Mhm.
I was just checking the MgS plus SROH2. Isn't is this like on the data sheet?
Uh-huh.
Is this alkali? Isn't like because I know that isn't the hydroxide often like including magnesium that is bonded with magnesium? Isn't that also supposed to be aqueous?
With magnesium, let's go look.
Yeah, because that's when I just wrote down.
Yep, let's go look. So hydroxide And you were asking with magnesium, which would be as the product, yes?
Yes, that will be the result.
Okay, so for strontium, it's soluble. That was one of our reactants, is soluble. And the alkalis are soluble, but magnesium is an alkaline earth. It's not an alkali ion. It's an alkaline earth metal.
Okay.
So your alkali ions, and like I said, don't be shy about writing them in. Lithium, sodium, potassium, rubidium, cesium, and francium. Or you can even just go lithium, sodium, potassium, rubidium, and leave off the last two because nobody ever uses the last two. So yeah.
So it's just an alkaline earth metal.
It's an alkaline earth, and because it is not one of the alkalis, it's not hydrogen, it's not ammonium, and it is not strontium, it would fall in the all others category and it would be low solubility. So that would be a solid. So MgOH2 would be solid. Yeah, just make sure that you're writing the correct formula. Don't just be, you know, smashing those ions together willy-nilly without balancing the charges. Be careful about writing your products, making sure that cations go with anions. You don't want to have two anions together. That would be bad news. Yeah, so just take care at every step along the way. And yeah, make sure you include your charges and your states.